So, let's start with probability. To a normal person, aka someone who is not an avid fan of quantum mechanics, probability is presented as a set of percentages, fractions, or even simple likelihoods. And yes, this is all applicable to macroscopic phenomenon, but now let's take a look at the microscopic quantum level, where one would find structures such as electrons, protons, neutrons, and even quarks. Here, probability is not a set number or percentage, but rather a graph, or more accurately, a wave function. Say we are looking to estimate the probability of a particle landing at point X, there is not a 50% chance we may find a particle at point X, but rather there are points that the particle is more probable to end up in than others. If we were to measure the position of the particle multiple times, we would get this result, with the identified positions matching the peaks of the graph. Now let's take a look at how this would apply to a macroscopic scale. So, I assume we have all heard of Schrödinger's cat, the famous thought experiment proposed by Erwin Schrödinger to mock the Copenhagen interpretation. We'll come back to that though. When the box is closed, there is a wave function which determines whether the cat-killing device is triggered or not triggered. When the box is opened and the cat is observed, either dead or alive, the wave function collapses into either the triggered or not triggered state. Before the cat is observed, it exists in a superposition of both dead and alive, meaning that it is technically dead and alive at the same time, assuming there is no other way to determine the cat's state. Schrödinger created this thought experiment to highlight the absurdity of the Copenhagen interpretation theorised by Bohr and Heisenberg, that of which was widely accepted at the time. Although it was an accepted theory, the wave function collapse suggested in the Copenhagen interpretation does not actually agree with Schrödinger's equations, the equations that outline all of quantum mechanics. This is where Hugh Everett and his many worlds theorem comes into play. He suggested that instead of the wave function collapsing, decoherence isolates branches of the wave function from each other. So instead of the cat being dead or alive, it is dead in one timeline and alive in the other. Not only is the cat split into two different timelines, but the whole Earth is split into as many different timelines as there are outcomes of the event. And not only is the Earth split, but the entire universe is split into an entirely new timeline, creating a multiverse of parallel universes. Even the smallest of interactions, such as virtual photons causing electrons to deflect, will cause the universe to split into an entirely new timeline. As you may have concluded, this leads to a near infinite number of parallel universes, growing in number exponentially as each second passes. Now this may seem ludicrous, but since the many worlds theorem suggests isolated branches of a wave function due to quantum decoherence rather than wave function collapse, it does in fact agree with more of the maths of Schrödinger's equations. I specify more as no interpretation agrees completely with the equations. All of them are still highly scrutinised and debated by many scientists. In theory, there could be as many interpretations as there are worlds, and we could still have no definitive answer. Now it is up to you to do your own research and discover which interpretation you agree with.